make sure this works. Okay, it works. I'll be on the side so you folks can see the slides, the content. So, hey again, thanks Ryan. My name is Panos Kampanakis and I work for AWS. AWS is a partner with Keyfactor, so some of AWS services are integrating with Keyfactor services in the back end in the cloud. So I'm here to talk about some common post-quantum signature use cases and their intricacies. And these are common, I mean, they apply to Keyfactor's use cases, AWS use cases, and everyone else's use cases for the most part. So before we go into the details, I want to summarize the signatures that we have available. So NIST has specified 2 new signatures, and there's one more specification that's coming out very soon. These are MLDSA, FNDSA, and SLH-DSA. All of these are quantum resistant. Does anyone know what FNDSA stands for? It does not stand for FNDSA. It stands for Falcon. So Falcon was the algorithm the name of the algorithm that was submitted initially. So these 3 signatures, for the most part, have good performance. So they're very close to ECDSA and RSA that we use today. FNDSA requires floating point arithmetic, some special instructions that are available on many CPUs. So for the most part, you know, FNDSA could be deployed at scale. SLH-DSA has slower signing and key generation. So these signatures, generally speaking, have good performance with the exception of SLH-DSA for signing and key gen. So the performance of these signatures is good. It's very close to what we have today. That's not the same with the size. So there could be some challenges related to size. So MLDSA and FNDSA have a few kilobyte bigger keys and signatures. So it's 1, 2, or 3, depending on what parameters you use. And that applies to keys and signatures. If we're talking about SLH-DSA, the public keys are small, but the signatures are bigger. They're 10 to 20, depending on the parameter. So, you know, it's frequently talked about that these signatures are bigger, the public keys are bigger, so we have to carry more data, and that could introduce slowdowns or performance degradation. So I'm going to talk about here about some common use cases and that impact. So the use cases that I'm going to talk about are artifact signing, like when you sign a document or a software or a firmware with these new signatures, and the intricacies that are related to artifact signing. I'll talk about transport auth, which is very common when we're setting up a tunnel and we use the new signatures for authentication. And I will talk about IoT a little bit, you know, because it's a little unique as a use case, at least the more constrained IoT applications. Before I dive into the use cases, I wanted to tease out a common requirement or need that Keyfactor's customers have, AWS's customers have, and everyone else's customers have, and that has to do with discovery. So, you know, we have all these keys, we sign stuff, you know, we issue certificates, but how will I know what keys or key pairs do I need to upgrade? Like, is there a repository or is there a way for me to know where I need to focus, where I have deployed these things that I need to upgrade? So, you know, I'm teasing Keyfactor Command here, but that applies to any type of lifecycle management solution or management solution. I have here the dashboard risk header in Command. So will it have a tile there that tells me these are the quantum vulnerable keys or certificates I need to upgrade, or the SSL scanner that's available in Command, or the dashboard collections that gives me the risks, or the risk assessment that Ted was talking about earlier. So there is a need for discovering these things, and I'm teasing Keyfactor Command and other third parties that offer such solutions. And that's something that we will need, and our customers will need, in order to prioritize the migration and not have blind spots, if possible. So don't ask me if these things are coming to Keyfactor Command. I don't have a clue, but go to Ted. I'm sure he's going to love it. OK, so let's start talking about the use cases. The first use case has to do with software signing, and I have MLDSA as the example here. So this is a typical use case where you have some piece of software, some document, or some firmware, and you want to sign it. So on the other side there, you have AWS KMS that can sign. It also integrates with Keyfactor, SignServer, and you also have some sort of PKI in order to provide the certificates for the verifier to verify the software signature. So basically, you sign your software, you send a request to sign your software. The example here is in the cloud, but it doesn't really matter. It could be on-prem as well. And the signing service will give you this new signature that will be carried together with the software for the verifier to verify it before loading up the software. So that's a typical software signing use case that we have. So let's talk about the intricacies or the challenges, the potential challenges that these post-quantum signatures will bring to that use case. So the signer needs to support these new things. OK, we understand that. The verifier, at the same time, needs to be able to consume the new signatures. They're slightly bigger. The public keys are slightly bigger, and also needs new code to verify the signature, right? Verification code for MLDSA or any other signature. For the most part, these are, the footprint of these things is a few kilobytes extra. So most verifiers will not sweat it. It will not matter. I mean, that's easy to implement in verifiers. So unless we're talking about a very constrained little IoT verifier that doesn't have enough RAM to load these new keys or signatures or code, verifiers will be fine in that use case. But there is an interesting intricacy here for that use case that has to do with downgrades. So there are common scenarios where you have a piece of software, but you don't control where it's going to be deployed. A typical example could be an operating system that you can deploy in an old legacy platform or an upgraded new platform. So in these use cases, because you don't control the verifier, it could be a legacy or a new one, you have to be able to support both of them. So if you want to introduce quantum resistance for the new software, like quantum signatures, post-quantum signatures, sorry, you basically frequently introduce two of them. So you have the classical ECDSA signature that legacy verifiers will be able to verify and load the software. But you also introduce a post-quantum signature. So the upgraded verifier is going to be able to verify a big quantum resistant. In some of these use cases, the upgraded verifier could verify both of them to do the hybrid signature scenario where, if you don't trust MLDSA, you do classical and post-quantum together. So, that's very common. It was done for Windows when there was a transition between SHA-1 and SHA-2, and you had two signatures, and the verifier chooses which one to use. So there is a concern for these types of scenarios where you have an adversary. The adversary has a quantum computer sometime in the future, and it can go back and strip the post-quantum signature from the software. So if you strip the post-quantum signature, it means that an adversary with a quantum computer could forge any software that they want and put a legit ECDSA signature, and that means that they can load anything on any platform, right? So that's a typical downgrade. You strip the post-quantum part, and you can break the classical part, and you deploy a downgrade. So that's a typical downgrade attack. And the mitigation is simple. The mitigation is that the post-quantum verifier has to look for the post-quantum signature. So the post-quantum verifier will fail unless there is a post-quantum signature in there. So the mitigation is simple. The legacy verifier, okay, it can still do ECDSA. Maybe it's dead in the water in terms of quantum resistance, but at least it loads the software. So the concern with these use cases is that some of these standards and their implementations that support these dual signature scenarios, they don't have the APIs, they don't have the support to be able to say, look for the post-quantum, and if it's not there, fail. They treat all signatures the same, right? So they use OR logic between them. So we would need some upgrades for these types of scenarios in implementations in order to support this new logic where it says, I want post-quantum or fail, or I want post-quantum and classical or fail for the upgraded verifiers. So that was the first use case, a unique downgrade type of concern that we need to be careful about. Okay, so the next set of use cases had to do with transport authentication. This is very typical. A lot of folks have talked about it, and we understand it well. So if we had MLDSA and or FNDSA signatures in these new protocols, their signing and verification performance is great. So it's like RSA today. We could deploy them. No one would see any impact in terms of CPU impact. But I have here a typical PKI X509 certificate that's used on the web. And it's showing there, if you see, the folks back there cannot see it, but it's a typical certificate. It has a public key at the top, and it has 3 signatures below it for SCTs and the CA signature. So if these fields are swapped to the post-quantum signature, like MLDSA, it means we will have many more bytes on the certificate. So, in a typical certificate chain that we use in our transport protocols, that means that we would see 10 or 15 extra kilobytes per connection. So when you're establishing this connection now, you have to send an extra 10 or 15 kilobytes before you do anything else, like before you transfer any data. So someone would say 10 or 15 kilobytes is a lot, right? It's going to affect my application, which makes sense, especially if you're in a slow network. 15 kilobytes matter. But will they matter? So I think the takeaway of this discussion here is that it depends on the application, so because applications have different intricacies. So the first application that I'm looking at, and no one can see what the page has. So the first application I have is the web. So the web, we're all browsing, we're all seeing things on our Instagram, and that's the typical use case. So I have an example here that's CNN.com, and I looked at all the connections that CNN.com opens. Like when a browser goes to CNN, all the connections that it opens. Because when we go to a website, there are many connections to fetch resources that we see on a web page. So you see there, CNN.com has a bunch of connections, all of these there, and the top one transfers 1 megabyte. So the top connection for CNN.com that transfers images, text, JavaScript, all things like that, had 1 megabyte in that connection. So will 10 or 15 extra kilobytes for MLDSA really affect the connection that transfers 1 megabyte? Probably not, right? Because 1 megabyte is a lot. So the top connection will not matter. And I have here another example. This is my favorite influencer that goes to the beach and takes a nice picture. So that picture usually is a few kilobytes, hundreds of kilobytes, or megabytes sometimes. These are high resolution pictures. So I think the point that I'm making is that for the web, the things we see are not of negligible size. They have decent size. So 10 or 15 kilobytes for these connections will not really matter because they do a lot. But okay, it's not as simple as that. You see down there are a bunch of other connections that CNN.com opens. And these connections are small. So down there I have a bunch of connections that do 5 to 10 kilobytes. So someone would say, oh yeah, these connections are going to suffer because they transfer 5 or 10 kilobytes of data, and now I have to do another 10 or 15 on top of it when I'm establishing that connection. So these connections will suffer. So what are these connections doing? Are they transferring content that I see, or are they doing other things? So I cannot talk about the whole internet, but I can talk about CNN. So in this example that I was looking at, there were many connections of these little ones that some examples are here that were transferring 8 kilobytes, 0 kilobytes, 7 kilobytes, or 6 kilobytes in these examples. And they were doing tracking, they were doing ads, they were doing user identity, and they were doing some marketing, web marketing things. So these connections, the lean ones, the slim ones, were not doing actual content that we look at. They were basically doing data, monetizing the web, right? Because there's a lot of monetization behind it. So the point is that if the web is doing a bunch of small connections that the user does not see, these connections are going to suffer, but the user is not going to realize it. So, I didn't do a whole study of the internet because that's challenging. We need more data on this space. But intuitively speaking, all this tracking and data that's being transferred in small connections for the web will suffer, but it will not affect the user as much. One more intricacy here that it was very interesting when I was looking at it is that we have CNN.com again, right? And webpagetest.org gives you a nice breakdown of the destinations that you visit, all the destinations you visit when you go to CNN. So all of these destinations here were fetching resources, like the browser was fetching resources for CNN. And as you can see there at the bottom, we have some metrics. These are metrics that affect the user experience. So these metrics here, FCP is the first contentful paint. That's the first thing the user will see, like the first little JavaScript little text or image. So the first contentful paint affects the user. The user sees something. The largest contentful paint, it's that metric down there, and that's the time that the user sees the biggest thing on the page. It could be an image, it could be anything. So FCP, LCP are metrics the user sees, experiences. The last one is the document complete time, and that's the time the whole page has loaded. Of course, the user notices that, right? When the page is loaded. So you see these metrics, these times here, that all of them affect the user, and you see all these little handshakes there. So all these are small connections that are getting established. They get a little data, and then they close down. So these connections, each of them would be affected by 10 or 15 kilobytes extra from MLDSA. And someone would say, okay, if each of these extra transfer times for the extra data is, let's say, 30 milliseconds, 30 milliseconds times 30 adds up. So it's going to affect the user a lot. The metrics are going to be pushed out 30 times this, right? So what's interesting is that here, some of these connections are parallel. That means that they don't affect each other. So it means that the impact on each of them is not additive to the metric itself. So if the connections are uncorrelated, you don't have to wait for one to finish for the next one to start, it means this parallelization here makes our lives easier. Like the 30 milliseconds is not additive per connection. So I guess the takeaway for the web is that the web is very complicated and each page is designed differently. But some of these examples here are showing that because they transfer a lot of data and because the small connections do not affect the user as much, and because many times they're parallel, the impact will not be as big as we would initially think. So, this is anecdotal. This is small experiments that I'm showing here. But, intuitively, we wouldn't expect this. And some folks think that because there's many connections, it means automatically MLDSA affects the web user experience by a lot. So that was very interesting when I was looking at it at the time. There are also some other use cases that will not be affected as much. They'll be smoother transition. So the first one is the client software use case, where you have machine-to-machine communications. So you have a client application, it gets terminated to some gateway, and behind it, there are a bunch of other applications, they talk to each other. So these connections now will have to do post-quantum authentication, means more data, and 10 or 15 extra kilobytes, right? So many times these connections, they transfer a lot of things. They transfer 100 kilobytes or more. And frequently, they're over fast networks. If you're in a 1 gigabps connection, 10 or 15 kilobytes will take very few milliseconds to transfer. So for these use cases where the bandwidth is great and there's a lot of data, MLDSA will not affect them as much, because MLDSA, it's only 10 or 15 kilobytes. So that's another example of a use case that will not sweat it. It will not suffer too much. A couple more use cases that will not suffer too much is VPN and SSH types of applications. The first one is a VPN connection that stays up for a long time. VPN connections get established, and they stay up for hours or days, and they transfer a lot of data. So will 10 or 15 kilobytes at session establishment for VPN really matter when you're staying up for a whole day? It will not, right? So VPNs will not care about 10 or extra 15 kilobytes. A similar example is SSH types of applications where you manage a bunch of instances through a session manager or through an SSH connection, or some SFTP transfer over SSH that transfers a lot of data. So these types of connections, they have a lot of round trips, and that's how the protocol works for SSH. So you have a lot of back and forths, right? And sometimes you have a lot of data through them too. So the time it takes to transfer an additional 10 or 15 kilobytes for these types of connections that have a lot of round trips, they will not matter. The user will not be noticing any slowness for the 10 or 15 extra kilobytes when it has to wait for a whole second to do the back and forth to bring up the connection. So these types of connections also will not suffer by a lot. So the last use case I had is a little intricate and a little sensitive. So not of all IoT use cases will suffer like the ones that I'm talking about here, because IoT is a very broad term. So IoT doesn't always mean constrained. But here, let's talk about a constrained use case. So I have some analytics platform that's collecting data on the right side, and I have a bunch of sensors that are collecting data on the left side, and they connect over some protocol, LoRaWAN or HTTP or MQTT, all these protocols that establish a secure connection, and they transfer the data to the other side. So in this example here, my sensor is measuring temperature and humidity. That's 2 bytes. So it wakes up, measures, sends them over, closes the connection. And it does that, every 3 hours, let's say. So these types of connections are small, they don't transfer a lot of data, and they're sometimes over constrained networks. So these are mediums where there's contention, there's low bandwidth, and all of these little sensors sometimes are fighting for bandwidth. So in these types of scenarios, 15 kilobytes matter. So the point is that if you have a constrained type of application where bandwidth is scarce and the connections are transferring little chunks of data and closing down, these use cases will suffer more, because there the 10 or 15 extra kilobytes have an impact. So there's an example of a suffering use case from the new algorithms. Okay, the timing is good. So the takeaways from this session, hopefully, are that use cases have different requirements and intricacies. So these new post-quantum algorithms may affect some, but there are many that will not suffer by a lot. These are the use cases that have decent resources, CPU resources, and they transfer big chunks of data over the network. The web use case on its own is very intricate and very interesting. It doesn't look like it'll suffer as much as we intuitively would think. And finally, we should pay attention to downgrades in all of our applications, because as we're migrating, we don't want to allow adversaries to bring us back to classical and deploy these types of downgrades. So downgrades are important for our use cases. That's what I had, and I think I did good timing.